Now we consider the question of whether this constitutes an inner product. The inner product of u and v should be u2v1 plus u1v2. The second component of the first vector times the first component of the second, plus the first component of the first vector times the second component of the second. Now, is it true that uv, the inner product of uv is equal to the inner product vu, the commutativity of the inner product? Well, we simply write out what this means. uv is this, same thing we have here. In vu, we've reversed the order of the two so that the second component of the first vector is now v2, and the first component of the second vector is now u1. And then the first component of the second vector, first component of the first vector is now v1. Second component of the second vector is u2. These are clearly the same, again, by the commutative law of multiplication. Okay, can reverse the order of both of these terms, and they'll be, then we'll have an expression identical to this one. Now, another property that we're going to test is whether u times v plus w, the inner product of u with v plus w is equal to the inner product of u with v plus the inner product of u with w. This is like a distributive law. It is a distributive law. I'll just put the word distributive with a question mark. That's what's going to hold if we can prove this to be true. To start with, we take the left-hand side. What do we mean by the inner product of u with v plus w? Well, that means just rewriting u and v and w, and I didn't have an arrow over my v, but rewriting u, v, and w as u as u1, u2, v as v1, v2, and w as w1, w2, this expression is equal to this expression. Just plain, simple substitution. Now, we want to add these two. We can add the two vectors, right? What's the sum of this vector and this vector? Well, that's just v1, w1 for the first component, v2 plus w2 for the second component. Did I say plus when I said this one? v1 plus w1, v2 plus w2. Now, what's the inner product of u1, u2 with v1 plus w1, v2 plus w2? Well, the inner product has been defined here to be the second component of the first vector listed. Okay, so when we do this inner product, we start with the second component of the first vector. The first vector is u1, u2. Here's its second component. Then it's times the first component of the second vector. Well, the second vector is here, and its first component is v1 plus w1, so we're going to multiply u2 by v1 plus w1. And to that we're going to add what? Well, first component of the first vector, second component of the second vector. So the first component of the first vector is u1, u2, so its first component is u1. And the second component of the second vector here is v2 plus w2. So the left-hand side comes down to this. And we could simplify this further, but I'm going to leave it here for the moment. Over here, we take the right-hand side and we write it out. Okay, so we simply write out what the inner product of u and v is. Well, we can just kind of copy that down from here. Then we have to think a little bit. If it's u and w, well, that one's pretty easy too. We're just going to replace v with w, so we're going to have u2w1 plus u1w2. Now, we have an expression for the left-hand side. We have an expression for the right-hand side. The question is, are they equal? And I'm leaving this just as an exercise. If you multiply both of these out, you're going to get 4 terms in each, and they will match up. So we can put this and this into exactly the same form. Or you can do some factoring. There are many ways that this and this can be put into the identically same form. And that then proves at least this property of the inner product for this rule.